Next type of intermolecular force is dipole-induced dipole interaction, in which a non-polar molecule may get polarized by the presence of a polar molecule near it, which makes an induced dipole. And the interaction between dipole and induced dipole is called dipole induced dipole interaction. Let us understand this with an example. For example, oxygen molecule. This is oxygen molecule, which is a non-polar molecule because both the oxygens have same electronegativity. And here this is a water molecule which have permanent dipoles, in which oxygen carries partial negative charge and hydrogen carries partial positive charge. When this permanent dipole, when this polar molecule approaches towards the non-polar oxygen molecule, then the oxygen molecule, the electron cloud of the oxygen molecule get distorted, get polarized. And one oxygen carries partial positive charge and other carries partial negative charge. And this is called the induced dipole. And the interaction between the positive charge of induced dipole and negative charge of water molecule is called dipole induced dipole interaction. Another example is of noble gases. Noble gases also get polarized in the presence of polar molecule. For example, helium gas, which get polarized by the presence of HCl molecule, or hydrogen molecule, which get polarized by the HCl molecule or water molecule. These are the examples of dipole induced dipole interaction. And these interactions, these forces was studied by Debye in 1920, and the effect is called induction effect. And the effect is called induction effect. Next type of intermolecular forces is dispersion forces or London forces. Why these are called as London forces? Because the origin of these forces was proposed by Fritz London. Fritz London, a German physicist. And after the name of Fritz London, these forces are called as London forces or dispersion forces. It is a temporary attractive force due to the formation of temporary dipoles or instantaneous dipoles in nonpolar molecules, or momentary dipoles in nonpolar molecules. These dipoles are short lived for a short time. As you can see in this figure, these are two momentary dipoles or temporary dipoles due to the unequal distribution of electrons, and these exist between the non-polar molecules, and they attract each other, and the attractive force is called dispersion force. For example, in case of noble gases like helium, In case of helium, suppose these two spheres represents the helium atoms. And this is the nucleus of helium, and the space around this nucleus have electrons. When they approach towards each other, a momentary dipole is developed in one of the helium atom, and its electron cloud get distorted like this. Here it is the momentary dipole. This momentary dipole induced a dipole in the other helium atom, and the electron cloud of other helium atom get distorted. These dots represents the negative charge. This is the negative charge, and the attraction between positive and negative charge of two dipoles, temporary dipoles, is called dispersion forces or London forces, and these forces are short-lived forces, and these London forces exist in polar molecules as well as in non-polar molecules. London forces are the only intermolecular forces that exist between the molecules. Magnitude of London forces. London forces are the weakest intermolecular forces, and their magnitude depends upon the following two factors. First is size and complexity of the molecule. Larger the size of the molecule, greater is the magnitude of the London forces. This is due to the large electron clouds, which are easily distorted or get polarized when the two non-polar molecules come closer to each other. When their sizes are larger or greater, they get easily distorted like this. Suppose these are two molecules having larger size and these are of smaller size. They get easily polarized when come close to each other. But here in small size, having small size, or they take some time to get polarized. Larger size means larger molecular mass. When we move down the group from top to bottom, the size of the atom increases or the size of the molecule increases. As the size increases, mass also increases. It means London forces depends upon the molecular mass. When molecular mass increases, London forces also increases. Mass depends on size, and when the size increases, mass also increases, molecular mass also increases. It means London forces also increases. And when size of the molecule decreases, molecular mass also decreases, and same for the London forces. London forces also decreases. For example, in case of CH4, SiH4, GeH4, when we move from carbon to silicon to germanium, the size of the central atom here, that is carbon, silicon and germanium, increases down the group. It means the molecular size of these hydrides increases as we move down the group. And when the molecular size increases, the London forces also increases. The magnitude of London forces also increases. And the next factor is geometry of the molecule. In geometry of molecule, the shape of the molecule larger the molecule, larger is the London forces. For example, in case of N-pentane, this is N-pentane, which is having a straight chain. This is N-pentane. It is a straight chain having 5 carbon atoms, and if and the formula of the N-pentane is C5H14. This is a condensed formula and this is the open chain formula. And the second formula is the neopentane, in which one carbon is in between the 4 carbon atoms. This is the formula of neopentane. This is neopentane, and the straight chain represents N-pentane. N-pentane is a straight chain molecule and neopentane is a branched chain molecule. Suppose it is in spherical shape like this, and in straight chain this is like this, and in straight chain there is larger area for interaction. We place two straight chain one over the other, there is larger area for interaction. But in case of branched chain, they acquire minimum surface area, means spherical shape, almost spherical shape, and the area of interaction is small. When the area of interaction is small, then the magnitude of London forces is also small. And when the area of interaction is large, then magnitude of London forces is also large. And that's why N-pentane has greater magnitude of London forces as compared to neopentane. Types of bonding and melting and boiling points. What is melting point? It is the temperature at which a solid melts to form a liquid. For example, melting point of water is 0 degree Celsius. Boiling point, the temperature at which a liquid changes into vapor form. For example, water has a boiling point of 100 degree Celsius. And one more point, that is triple point. Triple point at which the substance exists in all three states of matter, that is solid, liquid and gas. For example, water. Water exists in all three states at 0 degrees Celsius or 273 Kelvin, in the form of solid ice at 0 degrees Celsius, which is a freezing point of water, and at 0 degrees Celsius, this is also a melting point of water. It exists in a liquid form, and in 0 degree Celsius or 273 Kelvin, it also exists as a water vapors. It means water exists in all three states simultaneously at one temperature, and that temperature is called triple point. And how the bonding between the molecule affects the melting and boiling points. First, in case of ionic compounds. Ionic compounds have high melting and boiling points. Melting and boiling points depends upon the strength of bond, how strong the bond is between the molecules or atoms. For example, in case of NaCl, it has electrostatic force of attraction or ionic bond, which is the strongest bond. Due to this strongest bond, ionic compounds have high melting and boiling points. Next, in case of metals. Metals have metallic bonds. These are also strong bonds. Metallic bonds. And stronger bonds require more energy to break. That's why their melting and boiling points are high. Next, in case of covalent compounds, they show low melting and boiling points because covalent bonds are weaker than ionic bonds as well as metallic bonds, except in polymeric covalent molecules. Polymeric covalent molecules are those which form three-dimensional network. For example, diamond, in which carbon is tetrahedrally arranged with each other. And this tetrahedral structure makes the diamond hard and rigid. In this way, carbon is tetrahedrally arranged in diamond, which forms a hard substance, that is diamond, and it has highest melting and boiling point. And for simple covalent molecules, melting and boiling point depends upon the following factors. First is the nature of molecules, that is polar and non-polar molecules. Polar molecules have strong interactions. Polar molecules have strong interactions as compared to non-polar molecule. and polar molecules have high melting and boiling point than non-polar molecule. In non-polar molecule, London forces exist, which are the weakest intermolecular forces. Next is the size and complexity of the molecule. When there is larger size of the molecule, the magnitude of London force is also greater, and its melting point and boiling point also high. And when the size of the molecule is smaller, then the magnitude of London forces is also decreased. In this case, the melting and boiling points are low. Next is geometry of the molecule. If a molecule is of straight chain having no branches, then the molecules are closely packed to each other, and the interaction is higher in that case, and the magnitude of London force is also higher, and that's why they have high melting and boiling point as compared to the molecules having branches, in which there is less contact between the molecules and the magnitude of London forces is also less. Due to less force of attraction, they have low melting and boiling point.